fingertips. But here's the twist, the paradox we're diving into. Is our brain actually getting weaker? The more we lean on these tools, the more we outsource thinking?
It's what some are calling the memory paradox. And yeah, it's a critical question. We offload so much knowledge externally now. Think about it. Phone numbers, directions, basic
You
facts.
never have to remember them anymore.
Exactly. So what does that do to the internal structures, the very architecture of our minds?
And there's some, well, frankly, some pretty unnerving data starting to pile up. You know the Flynn effect, that decades-long trend of rising IQ scores across populations.
Yeah, it was a solid trend for a long time.
Well, it's stopped, and not just stopped in several places. High-income countries like Norway, Denmark, France.
Yeah.
The schools are actually reversing. They're going down.
Which is pretty alarming. So the core question for this deep dive, the thing we really want to unpack is,
Yeah.
could this be linked? Is our growing reliance on, well, cognitive offloading, as the neuroscientists call it,
Relying on external memory aids.
right? Is that, plus the big shift in education away from, basic memorization, is that combo actually undermining the very cognitive abilities we thought we were boosting?
We need to look under the hood, basically. See what's happening in the brain.
Let's do it. And maybe the first place to start is clearing up a really common misunderstanding.
Which is,
The idea that knowledge and skills are totally separate things. Like you can just learn critical thinking without actually knowing anything.
right, the skills versus contents debate.
Exactly. But neuroscience, and the sources we looked at are really clear on this, shows they're deeply intertwined. You can't have one without the other. They're two sides of the same coin.
Okay, so how does the brain actually build both? What are the systems involved?
Functionally, you can think of two major memory systems working together, or sometimes against each other if we're not careful.
Okay, give us the breakdown.
So first up, you've got your declarative memory. This is the system for conscious stuff.
Yeah.
Facts, concepts, general knowledge like remembering the capital of France or what happened yesterday.
Explicit memory, things you can state.
Right. And it's generally fast learning. The hippocampus plays a huge role here initially. You can learn a new fact pretty quickly. Think flashcards.
But there's always a but, isn't there?
The but is that recalling this stuff can be slow and effortful. It takes conscious work to pull it up.
Okay, so that's system one. What's the other?
That's procedural memory. And this one is different. It's the slow learning system. It's rooted in different brain areas, particularly the basal ganglia.
And this handles.
Skills, habits, automatic routines, things you do often without thinking, like riding a bike or typing or even speaking grammatically in your native language. You don't consciously think about verb conjugations. You just talk.
Or basic math facts, maybe? Like knowing 7 times 8 instantly.
Exactly. That's a perfect example. It takes a lot of repetition, deliberate practice to build procedural memory. But once it's there, performance is rapid, automatic, effortless.
And this is where expertise comes in, right? Getting things into that procedural system.
That's basically the definition of fluency and expertise. It's about moving knowledge from that slow, effortful declarative system into the fast, automatic procedural system.
Like the chess master you mentioned, the sources, they're not consciously calculating every single possibility like a novice.
No, they recognize patterns instantly.
Yeah.
It's become proceduralized for them. Or a mathematician who just manipulates algebraic expressions without thinking through every single rule each time.
And this isn't just metaphorical, is it? You can actually see this shift in the brain.
Yeah, you can. Brain imaging studies show that as someone gets really good at something, activity in the hippocampus, that declarative hub, actually decreases for that task.
And activity increases.
In areas like the striatum, part of the basal ganglia, that skill automation center takes over. It's a real neurological handoff.
Okay, so learning creates physical changes. Let's define a couple of key terms here from the source material. First, the Enneagram. What is that exactly?
The Enneagram is basically the physical trace left by a memory. Think of it as the specific set of strengthened connections between neurons that represent that piece of learning, like a particular wiring pattern.
So individual memory traces, but how do they link together to form useful knowledge? That's where schemata come in.
Precisely. If engrams are the individual wires, schemata or mental frameworks are like the whole circuit board.
Yep.
They're these larger, abstract, organized structures of knowledge.
Okay.
They link lots of different engrams together. So you have a schema for restaurant, for instance. It connects concepts like menu, waiter, paying the bill, different types of food.
And these schemata let you understand new situations quickly and make predictions.
Absolutely. They're essential for comprehension, for inference, for making sense of the world efficiently. Without good schemata, new information just feels disconnected. random noise.
Okay, so the goal of deep learning is building these schemata, often by moving knowledge into that fast procedural system through practice and struggle.
Right.
So what happens when we short-circuit that process? When we just reach for Google or a calculator the moment things get even slightly tricky?
Well, you disrupt that crucial process, that transition to procedural memory.
Right.
The basal ganglia, that automation center, it just never gets the practice trials it needs.
So the knowledge, like how to calculate a percentage or remember a historical sequence, it just stays stuck.
It stays stuck in the slow, effortful declarative system. Or worse, it doesn't even get properly encoded there. It just lives in the external tool. It creates a bottleneck. You can find the answer, but it's slow, and you haven't internalized the process.
And this bottleneck has bigger consequences, doesn't it? This idea of cognitive load.
Yes, this is huge. Your working memory, the mental space where you actively juggle information, is very limited.
Like RAM on a computer.
Kind of, yeah. And if you haven't proceduralized the basic, say, multiplication facts or basic grammar rules or key definitions in a subject, then just performing those basic mechanics eats up all your working memory capacity.
So there's no room left for the actual interesting part, the higher level thinking.
Exactly. That high cognitive load just chokes off higher order cognition. You can't synthesize complex arguments. You can't solve a multi-step problem. You can't be creative if all your mental energy is bogged down in the mechanics.
Which explains why that initial struggle, that practice, is so important. It frees up mental bandwidth later.
It does. And neuroscience goes deeper, explaining why struggle is key. It comes down to something called prediction errors.
Okay, what's a prediction error?
It's basically the mismatch between what your brain expects to happen and what actually happens, the surprise signal.
Like, I expect 5 times 10 to be, I don't know, 60 for some reason, but the answer is 50. That feeling of, oops, wrong.
Exactly that oops moment, that surprise triggers a release of dopamine in the brain. And that dopamine acts like a save button or maybe a pay attention and fix this signal.
How does it do that?
It essentially creates what are called eligibility traces. It tags the neural connections that were active just before the error was detected, marking them for strengthening or weakening. It's a form of reinforcement learning. We literally learn best when we're slightly wrong and realize it.
But here's the catch, isn't it? To have a prediction error, you first need to make a prediction.
Bingo. That whole system hinges on you having an internal expectation. You need those internal schemata, even if they're imperfect, to generate that prediction in the first place.
So if I always use a calculator for 5 times 10, I never generate my own internal prediction, even a wrong one.
Right. Your brain doesn't predict 60 or 50, it predicts nothing. It just waits for the external tool. So when the calculator shows 50, there's no mismatch. No surprise.
No dopamine signal.
No dopamine signal, no error correction, no learning signal gets fired. You effectively bypassed the brain's natural learning mechanism by outsourcing the initial thought. Convenience actively prevents the internalization.
Wow. Okay, that links directly to the bigger picture, the societal shift. If struggle and prediction errors are so vital, why did education, especially in the West, move away from things like memorization, drills, practice?
Well, it was partly a reaction, starting maybe mid-70s onwards, against what was seen as rote learning or drill and kill. The idea was to focus more on higher-order thinking, critical thinking, learning how to learn.
And this timing coincides with
The rise of cheap calculators, then personal computers, then the internet. The technology made it possible to offload, and the educational philosophy seemed to endorse it with that appealing mantra. Why memorize it when you can just look it up?
But looking it up constantly has cognitive consequences. You mentioned digital amnesia earlier, the Google effect.
Yeah. Research shows pretty clearly that when we expect information to be continuously available online, we make less effort to encode the information itself deeply.
So what do we remember instead?
We tend to remember where to find the information, the search terms we use, the website, the file path. It's like creating a biological pointer to the data rather than storing the data itself.
I definitely feel like I do this. I know how to find something again, but I don't actually know it internally.
And that creates this dangerous illusion of knowledge. You feel competent because the answer is always just a click away. But your internal schemata, they remain weak, impoverished.
So if the internet goes down or you need to connect ideas spontaneously,
You're stuck. You can't reason flexibly. You can't synthesize information from different domains because the underlying knowledge isn't actually in your head integrated.
And connecting this back to the Flynn effect reversal, the drop in IQ scores, the timing seems suggestive, doesn't it?
It's hard to ignore the correlation. The cohorts showing these declines are largely those who went through schooling, during the period when digital tools became ubiquitous and educational focus shifted away from foundational knowledge mastery.
And it's not just a general drop in intelligence, is it? The studies pinpoint specific areas.
That's right. The declines are often sharpest in areas like vocabulary, reading comprehension, general knowledge, things that rely heavily on having rich, well-connected internal knowledge structures. It points towards a reduction in, well, practiced cognitive skills.
Which brings us right up to today, and generative AI like ChatGPT. This seems like cognitive offloading on steroids.
It definitely presents a new level of challenge. Early research is already showing something worrying. Students who use these AI tools to help with complex tasks, like writing essays or coding.
They often produce better results, right? The essay sounds better, the code works.
Often, yes. But here's the kicker. Studies are finding that these students show little to no learning gains afterward, compared to those who did the work themselves. They haven't actually improved their own skills.
Why not? What's the AI doing, or rather, not doing for their learning?
It seems to enable what researchers are calling metacognitive laziness. The AI does the heavy lifting, structuring the argument, finding the right words, debugging the code.
It bypasses the struggle?
It bypasses the essential mental effort. The trial and error, the grappling with confusing concepts, the reflecting on why something didn't work, the integrating of feedback, all the messy stuff that actually builds those lasting engrams and strengthens schemata.
So the AI gives you the fish, but you never learn how to fish. In fact, you might forget how if you rely on it too much.
That's a good analogy. The goal shouldn't be to ditch technology entirely. That's impossible and probably undesirable. Offloading some things is fine, using a calendar, making notes. It's about augmentation without atrophy.
What's the dividing line? When does offloading become detrimental?
It's when it replaces the initial learning and internalization phase, especially for foundational knowledge and skills. Experts, people who already have strong internal schemata, can use tools like AI brilliantly to amplify their abilities. But novices who offload everything from the start, they never build the mental maps needed for independent thought.
Okay, so if we want to avoid this cognitive atrophy, how do we find that balance? Are there practical, evidence-based strategies?
Yes, absolutely. Neuroscience gives us some good pointers. One key idea is optimizing the level of challenge during learning. This relates to the 85% rule.
85%, what does that mean?
It suggests that learning is most efficient when you're succeeding about 85% of the time during practice. That means you're getting about 15% wrong.
So, not too easy, not too hard.
Exactly. It's a sweet spot.
Yeah.
Enough success to stay motivated, but enough errors to trigger those crucial prediction error signals that drive learning without causing complete cognitive overload and frustration. It echoes older ideas like Vygotsky's zone of proximal development.
Makes sense. Keep it challenging, but manageably so. What else?
We need to embrace desirable difficulty. This means making the brain work to retrieve information. Things like active recall practice testing yourself instead of just rereading notes.
And spaced repetition. Coming back to material just as you're about to forget it.
Yes.
Yeah?
Both of those force retrieval effort, which is what actually strengthens the engrams over the long term. Passive review is far less effective.
And how should we think about using technology then? Like calculators or AI tutors?
Critically, they should be used as supplements, not substitutes for that initial effort and internalization. There was a great example in the source material about an AI math tutor using Ghana.
What made it effective?
It didn't just give students the answers. It provided scaffolded practice hints, prompts, targeted feedback, encouraging them to actively engage, make mistakes, and correct them. It supported the learning process. It didn't bypass it.
So the aim is to build those internal maps first.
That has to be the objective. Cultivating learners who have truly internalized the fundamentals, the core facts, the key procedures. Building those robust schemata inside their own heads.
Because that's what allows for real understanding. Flexible thinking, synthesis, independent reasoning.
Yes. Only once you have that solid internal foundation can you really leverage technology effectively, using it as an amplifier for your own well-developed cognitive abilities, rather than a crutch for underdeveloped ones.
So the core message seems to be, internalizing knowledge isn't old-fashioned, it's essential.
It truly is. We remember what we wrestle with. We understand what we internalize. Storing foundational knowledge isn't just about trivia, it's a fundamental pillar of how our cognition works.
Okay, let's leave our listeners with a final thought to chew on, something maybe a bit counterintuitive. We often think you need to be interested in a subject before you'll put in the hard work.
Right, that passion comes first.
But maybe it's the other way around. Maybe that lasting interest, that real enthusiasm, often only emerges after you've pushed through the initial difficulty and started to gain some competence, some fluency.
So by skipping that foundational grind,
Yeah.
that desirable difficulty,
We're not just making ourselves less knowledgeable, we might actually be robbing ourselves of the chance to develop deep, satisfying expertise and the genuine passion that comes with it. We might be short-circuiting the very reward system that makes learning feel worthwhile in the long run.